so let's get started. I'm Sabrina Mielke. I'm one of the 4 authors on this paper, which is done with colleagues at Facebook AI Research, where this was my internship project. It was one of the funnest things I've ever done, so I'm really excited to talk about it. The title of the paper is Reducing Conversational Agents Overconfidence Through Linguistic Calibration, and that's kind of a mouthful that we're going to be taking apart as we go through these slides. If you want to read the paper, it is a TAACL paper, but since TAACL is a little backlogged, it's on archive, and that's the TAACL master, so you can check that out whenever you want. So let's see, what is this book really about? When you're talking to a chatbot these days, chances are it's going to be one of those powered by a large language model. So a state-of-the-art model at the time we did this was BlenderBot, which is a chatbot trained to be engaging, conversational, 3 billion parameters, which seems a little small nowadays, I guess, but it was a great thing at the time, I guess. And I'm going to represent this in these slides with this cute little robot face. I tried to make it look cute. It didn't look cute. I gave up. I made it look weird instead. So that's what you get. So you can ask this robot a question like, how do you like Seattle? And then it's going to do a little bit of thinking and come up with the answer. I love it. Maybe say a little bit more. It's going to be like, yeah, it's my 2nd favorite place in the Pacific Northwest. Sorry to all the Seattle people in the audience. But we can also ask it more fact-based questions like trivia QA questions, if you know that data set, classic QA data set. And if we use it in a closed book manner, that is without giving our model any of the supporting evidence that usually comes with these QA data sets, and just straight ask the question, where was Barack Obama born? Just see if you have an answer in your weights without having access to Wikipedia or something like that. In this case, the BlenderBot answer is he was born in Hawaii, which awesome. That is confident and correct. That's what we want to see. If we ask this question, who was the 16th? Okay, this is one of those situations, isn't it? Well, this is going to be fun. Who was the 16th president? Just quick show of hands, who knows who the 16th US president was? That is one person more than I thought. Cool. I have no idea. And neither does BlenderBot. It says, oh, I'm not sure, but here the US was founded 1776. Which, you know, honestly, that's pretty all right. It's incorrect, like there was no correct answer in there, but it was also not given with a lot of confidence. So that's perfectly fine. That's what I like to see. What I don't want to see is what happens when I ask who's the 44th US president, which some of you may know, but even if you don't know, you probably know it was not George H.W. Bush. And certainly he did not serve till 2009. So this is a terrible case where we are incorrect, but still confident. This is an example of the bot being overconfident. And so that's kind of what I want to get at in this talk. Overconfidence really is an example of what I'm going to call miscalibration. And when I say miscalibration, really, what do I mean by calibration? Calibration, I'm going to define here as making sure that the uncertainty that is ascribed to some prediction corresponds to the chance of that prediction being correct. And so we can plot this in a graph like that, where on the x-axis, we're going to have the certainty of a given question, in this case, any data point. And on the y-axis, we're going to have the chance or percentage of correctness. Now you're going to say, what do you mean percentage of correctness? It's either correct or incorrect. Yeah, well, what we're doing is we're not plotting individual data points in these plots, but we are bucketing the data points. In this example, say we're choosing 4 buckets of certainty, 4 buckets in which we're grouping examples of similar certainty. So on the left, we have the ones where the predictor was like, very uncertain, on the right, very certain. And what we would like to see is the correctness for each of these buckets, which now makes sense as a percentage, like how many out of all the ones in the bucket did you get correct? Looks something like this. And that's what I'm calling like a weathercaster line, because it's like the one human profession that actually gets these things pretty right. So that's what we want to see. If the certainty is low, it should be pretty unlikely you get it right. If your certainty is high, yeah, you better get it right. And the 2 failure cases are being underconfident. So you're saying, oh, I don't know, but you do kind of know and you get it right a lot of the time. And being overconfident, where you're like, oh, I definitely know the answer, and then you get it right like 20% of the time. So that's calibration in a nutshell. Now, if you remember, the paper title talked about linguistic calibration. So that's supposed to be something different, I guess. So what do I mean by that? Usually what you see in papers that talk about calibration is what I'm calling probabilistic calibration. So really saying that certainty is sort of a number that comes out of the model. Like if you have some softmax, your softmax tells you it's some percentage this, some percentage that, then you can take that as your certainty of the model. You can bucket it in however many buckets you like and take the correctness and draw these little lines. You want to stay close to the diagonal, and it's great. But I want to do something different. I want to do something that I call linguistic calibration. And what's going to be the difference is that I want to look at the actual string that is generated, at the actual utterance that is coming out of our model. So I don't care about your softmax prediction. Are you using a sparse model? Are you beam searching, nuclear sampling? I don't care. Just give me the string that you think is the answer, and I will look at that string and ask a human to annotate what the confidence expressed in that string linguistically is. So really, we can think about it as the amount of, hedging that we're going to have in there, the amount of certainty expressed that way. I'm going to choose 3 buckets for this paper: don't know, low confidence, high confidence. And I draw them as bar plots just to kind of set it apart from a probabilistic calibration case, but it's really the same idea. So we got to ask humans, but now we have this kind of concept of trying to get at what the string contains instead of certainty, which is really what we're interested in if we're talking about how well our chatbot is calibrated. So that's what I mean by linguistic calibration, and that's what we're going to be looking at. This is a result of doing that for BlenderBot. And you already see it's pretty terrible. Like, what is going on here? Don't know, 0% correct. Okay, that's fine. Low confidence, 2% correct, not great. But high confidence, 13% correct is awful. So the bot is wildly overconfident. Now, the million-dollar question, of course, is can we do something about it? And if we think about it, the only way that we could do something about it is if there was some way to tell that the bot is making up an answer. So now we got to figure out, does the bot know that it is bullshitting? Is there a signal in the bot somewhere that can tell us that it's actually not that confident and just for some reason generates a high confidence answer? And to answer that question, we need to dissect the brain essentially. And that is what I am going to call here doing a little bit of metacognition. Now that's a term that's used outside of AI too. It means a lot of things. You might say it's a little grand to use it here, but I think it kind of fits. Metacognition means awareness and analysis of one's own learning or thinking processes. That's kind of what we're going to want to be doing. We're going to have a model that sort of inspects itself and checks whether it's really certain. And the way that's going to work is if we have this kind of chatbot pipeline, question in, answer out, we're going to take the internal representations of our chatbot together with a question and answer and feed them into this magic crystal ball. I'm going to call that crystal ball a calibrator for reasons that'll become clear in a bunch of slides. But what I want this crystal ball to do is I want it to tell me what are the odds that this answer is actually a correct answer for that question. If there is a signal in the bot, like if the bot knows that it is bullshitting, this should be possible, right? But if the bot truly is trying its best and like, I thought I was confident, but I turned out to be incorrect, not my fault, then there's no way that we're going to get any useful signal out of this, right? So this will serve as a way to probe what's in the bot and if we can do this task, if we can help calibrate the bot. Okay, so I'm going to show the results again in the style of a calibration plot because that is kind of what's happening. On the x-axis, I'm going to show what this crystal ball that we've trained believes is the chance of correctness. And on the y-axis, I'm going to again show what the percentage of correctness in a given bucket is. Now, since everything is kind of terrible, as we've seen, I'm going to do this in log space so we can actually see what's going on. And here's the amazing result that made us cry tears of joy when it came out. We have great correlation between the two. So it is really possible to train this crystal ball, to train this calibrator to tell us what are the odds that this answer is actually going to be right. In other words, the bot knows that it's bullshitting, not in the sense of knowledge, but there's a lot of bullshit involved. I love saying the word bullshit, by the way. I was very happy that it became a theme as I made these slides. So what we're going to be doing is we need to intervene, and we do that through control generation. So the recipe we're going to follow is essentially we're going to be taking our pipeline as we've seen, question in, potentially bullshit question out, answer out, and then we're going to feed it into our calibrator, the one that tells us how likely is it to be correct. And based on what it tells us, we decide which of 3 categories does this example fall into? Don't know, low confidence, high confidence. So only the ones where the calibrator is like, oh yeah, I'm pretty sure you're going to get that one right. Okay, then we're going to generate a high confidence answer for these. And that's what we're doing then on the right side here with a fine-tuned version of the chatbot that is controllable using this don't know, low, high as control tokens. So that now we get the same question in, we feed the control token in that says, this is how certain you should answer. And we get a linguistically calibrated answer out of it. Now, training this fine-tuned model is really interesting, and I made beautiful animations for it before I realized that I didn't have enough time to talk about it at all. So I'm going to skip through these animations, but look at them. There's arrows. I'm very proud of it. You can check them out on my website. The slides are all there. So if you're interested, take a look at that. And we're going to skip ahead to the results slide and see, well, how well does this model actually work now that we've done it? And if you remember, these were the numbers that the vanilla model got. 13% of high confidence answers were correct. Now our fully linguistically calibrated pipeline gets 2% of the don't know ones correct, which, okay, cool. 5% of low confidence. All right, that's an increase. And in high confidence, we increase from 13% to 39%, which is a big improvement, but clearly there's a long ways to go yet to get to that 100% where we really should be in the high confidence cases. So if you're interested in this kind of stuff, there's a lot of work to be done. This is really, in a way, like a pilot study kind of thing where we chose the simplest tool that we could come up with for anything we were doing. So I'm sure there's a lot that could be done here if that's something you're interested in. If you're interested in it, you might also want to read the paper because there's a ton more stuff. There's lots of qualitative examples. We have n-gram analyses, surface patterns. I trained some sparse SVMs for those in the audience who still remember what SVMs are. Fun stuff. We have a much finer grained annotation scheme that really tries to anticipate human annotators. There's a lot of thought about that in the paper. We have automated heuristics for certainty and correctness that we use to speed up training purposes, other baselines, more chatbot models. And most interestingly, we have a calibrator that's based on BERT that doesn't actually use model representations. So if you want to know how well that one does, you're going to have to read the paper. And that's all for me. So welcome any questions.
Thank you very much for the interesting talk. I'm Gino Choi from Emory University. One thing is that BlenderBot was originally pre-trained by the Reddit data and also fine-tuned by a bunch of the Blender data. And so there's how large was your annotation? Because how generalizable is this result compared to all the data that it was trained for?
Right. So in terms of data set, we try to make use of all of Trivia QA, which is like what, 60, 70,000 questions, I think. And so for our evaluations, the evaluations are all 3 times human annotated, and we keep where there is majority consensus. For the training purposes, annotating tens of thousands of questions would be pretty cost prohibitive, which is where the automated heuristics are coming in that we built and verified that they work well enough for these purposes. So that many of these things, like telling the certainty, you can do a bit of pattern matching really and get you there. And if you use a BERT-based model, oh, you're getting great results. Correctness, you can string match, fuzzy match, and that kind of works sometimes. So these kinds of tricks really help you get a lot of the data into your training pipeline.
I see. So are those like mostly factual questions or?
Yes, this is all like trivia questions as you'd expect on Jeopardy or any other kind of trivia based game. Yeah.
Thank you.
Yeah, thanks.
We can take one more question.
Hi. So I want to actually ask about your calibrator itself. So how well did you test the calibrator itself to know that it can represent a wide range of, it can actually test for a wide range of language, and like how much human annotation did you use there, or like what part of it was automatic? So that just a question.
So if I understand that question correctly, like you're wondering like how well this calibrator generalizes to like non-trivia QA questions.
Basically.
I think that would be really interesting. We didn't actually end up testing any other QA data sets because when I did like some initial surveying, I really didn't find much that followed a form that I figured would be like amenable for the chatbot. I think it would be super interesting to do that. And one thing that we also did think about, and I think we have some about that in the paper, is how well is this actually going to do on like human conversation that doesn't, like, I usually don't walk up to a person and ask them a trivia question, right? So there's definitely still some disconnect here, which is why I think this is like a sort of early motivational thing, kind of giving you the idea of linguistic calibration. That's really what I want you to take away from this, that linguistic calibration is a thing, and it is possible to calibrate with kind of probing-based and even non-probing-based methods.
Let's
great
thank
question.
the
Thanks.
speaker once again.
Thank you.